Sigmoid versus Tanh. In the last few lectures, we discussed about two different activation functions. The first one was sigmoid activation function and the second one was tanh activation function. Keep in mind, this is hyperbolic tangent, not the normal tan that you learn from trigonometry. This is from hyperbolic trigonometry. Let us understand how are these two functions different, what are the similarities, and also we'll see how you can derive one from the other. Okay, this is what we are going to learn in this lecture. Mainly you want to understand what are the differences and how are they behaving as an activation function. First thing is, both these are having S shape, that is sigmoid shape. This shape is called as sigmoid. Both sigmoid function as well as tanh function both are having sigmoid shape. Let us just draw the graph. We already did this in the last few lectures, but let us draw this again and understand. In case of sigmoid function, let me take a color here. Sigmoid will look something like this. It is going in sigmoid shape like this. So if I put the values here, it will be starting point. This will be 0. This will be 1 where it is having peak value. In the middle at 0.5, it will be meeting the axis. Okay. Let us draw tanh as well and then we'll see to it. Tanh will be something like this. It will start here, go through the center and again saturate at 1. So this is tanh. So this is tanh x and the first one it is sigmoid. This is sigmoid of x. These are the functions. First thing you have to understand here is your sigmoid function, it is not zero centered. It is centered at 0.5. So it is not a zero centered function. And what does tanh function do? It takes care of that problem. It is a zero centered function and hence one major drawback of sigmoid is taken care by tanh function. But this does not mean tanh can be placed exactly in place of a sigmoid. So that is what we are going to see. Where to use sigmoid, where to use tangent and how are they different. Okay. So first of all, we'll just write the formula so that everything is clear. Sigmoid can be written as sigmoid of x is 1 by 1 plus e power minus x. This is the formula for sigmoid. We already know this. And what about tanh? Tanh function, tanh of x, this has the formula e power x minus e power minus x divided by e power x plus e power minus x. So these formulas also you will be familiar with. The remaining steps we are going to discuss are the differences between them and how to derive one from the other. These two are the things we are going to discuss. First thing, the range of these functions. Sigmoid, you know, it has range from 0 to 1 and tanh has range from minus 1 to 1. This is why this is 0 centered, but this is not 0 centered. So from this point, I want you to think intuitively and understand when will this be useful and when will this be useful. Simply saying 0 centered, we already discussed it in previous lectures, but I want you to think and understand what is the advantage of this particular range 0 to 1 and what is the advantage of this particular range minus 1 to 1. So the advantage goes like this. Sigmoid is suitable whenever you want the output to be considered as a probability. This is when you go for sigmoid. For example, if you have a lot of layers in your neural network and from the final layer, whatever output you're getting, you want to take it as probability of one particular class or something, then sigmoid is a better option because here you can consider it as a probability. So generally you can say for output layer in such classification tasks and all, sigmoid is a good option because you can interpret this value which is between 0 and 1 as a probability. This is why sigmoid becomes a good option in such cases. What about tanh? If you think about tanh, in all your hidden layers, that is not the output layer, in the hidden layers in between, tanh is a better option. Why is it? Because in these cases, you want zero centered activation and you want bounded activation. So if you see tanh, it will take value from minus 1 to 1 and it is zero centered. So in this case, for all your hidden layers, tanh is a good choice for activation. And coming to the output layer, if you want to treat it as probability, sigmoid will be a good choice for activation function. So another way I can put this is, you can see tanh function as a new version of sigmoid. That is, the shape of function is same, everything is exactly same. The only difference is it is centered at a different point. Instead of 0.5, it is centered at 0, and it is, you can say, slightly rescaled. So you can see it as a rescaled and shifted version of sigmoid. That is how you can see tanh. Both are very similar functions, just that tanh is a rescaled and shifted version of the sigmoid function. Okay, so one more thing, when you use this in intermediate layers, how are you going to use this in back propagation, and how are you going to use this in forward propagation, and how does it make sense for you? So in back propagation, one thing you want is each gradient's value, that should be proportional to the derivative of output, because taking the derivative, you are going to find the gradient here, and then using that gradient you are going to update. So you want to see how much is this output going from here, and how is it contributing to the loss, and then when you are back propagating, you want to see what part of that loss is contributed by this particular neuron, that is weight in that particular neuron, and accordingly you want to update the weights. So for this purpose, one thing you want is, if let us say all your outputs are positive, then what happens is all your gradients will be one-sided. We discussed this already in the sigmoid lectures, that all your gradients will be one-sided. If that is the case, then your convergence will become slower because of zigzag updates. Instead, if all are not positive, instead if it is the case that your outputs are sometimes positive, sometimes negative, then all your gradients won't follow the same direction. Instead, gradients will not be one-sided, they will not be biased. So it's better for convergence in an optimization algorithm. So that is another reason why I would say use tanh in the intermediate layers. But in the last layer, output layer, if you want a probability as output, it is good to go for sigmoid activation. Okay, so you can say tanh solves the problem of not being zero centered. When you have negative input, you have negative output from tanh. When you have positive input, you have positive output from tanh. And this is the zero centered behavior that we are having for tanh. So you have faster training, faster convergence, better optimization. That is what you get with tanh function. Next thing is, can we try to see a relationship between tanh and sigmoid? Is it possible to derive sigmoid from tanh or tanh from sigmoid? So actually both are possible. What we'll do is, we'll take tanh and try to see how you can express in terms of sigmoid. Okay, so this will be an interesting exercise. What we'll do is, first we'll write the formulas here. If you take tan hx, okay, tan hx, if you take this function, you know it is e power x minus e power minus x divided by e power x plus e power minus x. How can you change this? If I want to change, I will multiply both the sides by e power x. That is numerator and denominator, both if I multiply with e power x, then what happens? You will get e power 2x minus 1 divided by e power 2x plus 1. So here e power minus x into e power x will be 1. Okay, that is why this is the value. Once you get this, next thing you want to do is, I want to have some relation with sigmoid. So sigmoid, I know it is 1 by 1 plus e power minus x. I should be trying to bring this value somewhere inside this. This is the target. What should I do for this? What I'm going to do is, you know this is sigmoid of x. That means what will be sigmoid of 2x? This can be written as 1 by 1 plus e power minus 2x. That is, here instead of x I put minus, instead of x I put 2x here. This can also be written as, if I take the 2x to the numerator, e power 2x divided by e power 2x plus 1. So I'm trying to bring it to this form, okay, so that I can correlate both. Next thing is, now I got this form. You keep thinking how I can take this form to something closer to this and express tan h as a function of sigmoid. That is what I'm trying to do, okay. So if this is the form, what can I do from here? This is the next question. I want to bring it to this form. So what I'll do is, if I take, okay, if I do 2 sigma of 2x, then what I get is 2 times e power 2x divided by e power 2x plus 1. Okay, I'm keeping this here. Then I will bring this back to this form. Then we'll add both. Okay, keep this particular result here. What I'm going to do now is, instead of this, what if I do tan h x plus 1? Then what I'm going to get? That is, if I do tan h x plus 1, that would mean whatever is here, that plus 1. So e power 2x minus 1 divided by e power 2x plus 1 plus 1. This is what I'm going to do. So instead of 1, I can write e power 2x minus 1, e power 2x plus 1 by e power 2x plus 1. If I solve this, I will get 2 times e power 2x divided by e power 2x plus 1. That is, this minus 1 and this plus 1, they get cancelled. So what remains is 2 times e power 2x divided by e power 2x plus 1. Are you now able to see some relation here? What I got here and what I got here, these two are one and the same. So I can equate these two. How can I write? I can say tan h of x plus 1 is same as 2 times sigma of 2x. So whatever I found here, that I equated with this, because both the values are equal. Both are 2 times e power 2x divided by e power 2x plus 1, which means both these are same. So how can I write this? I can say either I can say tan h of x can be written as 2 times sigmoid of 2x minus 1. This is one way. Or I can also say sigmoid of x can be written as tan h x by 2 plus 1 by 2. So both are the same. Okay. The same thing can be either written as this or this. So generally we use this one, that is tan h can be expressed as a function of sigmoid. So I just wanted to show that tan h and sigmoid are related in this way. So tan h can be expressed as 2 times sigmoid of 2x minus 1. So this is where tan x and sigmoid are different. They have different use cases. If it is a neural network perspective, from there you can say for output layer for a classification task or something, if you want probabilities as output, sigmoid would be a good choice for output layer. But for the hidden layers, tan h x will be a better choice.